Hi, I am Junlei. Thanks to my co-authors, Tobias, Jonathan, and Holger, for allowing me to present our research. Today, I would like to present to you our work, Visual Noise Cancellation, exploring visual discomfort and opportunities for vision augmentations. Our work takes inspiration from the rise in audio noise cancellation, and we propose that it is now time to embrace the concept in the visual domain. We see a lot of situations that potentially introduce visual noise or discomfort, which motivated the need for our work. For example, the flicker is often associated with uncomfortable feelings, especially those who are photosensitive. The bright headlights annoy drivers when driving at night. People walking around and talking also distract. We wonder if we can do something similar to audio noise cancellation headphones, but in the visual domain to remove those visual discomforts. We searched in the community to find if there is any existing work that investigated visual stimuli that are perceived as uncomfortable or worked on removing certain visual stimuli. However, the few identified works do not explore the general characteristics of visual noise, but target specific applications. For example, Gordon Westing's work has a mainly technical character and investigates technical means to modulate brightness. Masaki Koshi's head modulates the visual periphery by blurring the background to increase focus, and there are other similar works modulating visual silencing from within the augmented human research community. Luanne Boyd is an example of work with an origin in psychology that manipulates image luminance to improve eye gaze and verbal behavior in autistic children. Shohei Mori's survey presents an overview of diminished reality that generally aims to remove certain sound features, including those that could potentially be distracting. However, as indicated before, we are not aware of a general exploration of visual discomfort and how to address it using computing technology. In fact, there seems to be a general research gap on what people perceive as visual noise and what causes visual discomfort. Our work mainly addresses two questions: what is visual noise, and how could we do for visual noise cancellation? Let's start with the first one, understanding visual noise or visual discomfort. To understand visual noise, we ran 4 workshops with a total of 17 participants, following ideal brainstorming rules. The main inclusion criteria for our workshop recruitment is either a background in HCI, graphics and design, or psychology, but also from the general population. For example, Workshop 3 consists of 2 photographers, a psychology expert, a design expert, and a photo printing company worker. We first introduced the workshop steps to participants. Then, we asked participants to write down their visual noise scenarios and share them with others one by one without discussion. After that, we have a discussion session where everyone can express their opinions about those scenarios. Again, we repeated these brainstorming steps but changed the topic from visual noise scenarios into visual noise categories. Finally, we collected 31 categories and 120 scenarios. There are many interesting ideas. However, there are also many similar descriptions. Here I give some scenario examples to give an overview of the workshop result. Participants from Workshop 1 thought cold light in a hospital is visual noise. Participants from Workshop 2 mentioned rain is also visual noise. In Workshop 3, participants from a psychology background described that decoding signs can be cognitively overwhelming. One participant from Workshop 4 gave a reverse thinking that those objects that people want to see but can't are also visual noise. Based on those scenarios and categories, we then ran a convergent discussion among the authors to refine ideas. We agreed to not create any new ideas instead focusing on refining ideas provided by the participants throughout the workshops. Although there is no evaluation of good or bad ideas in the brainstorming steps to encourage ideas, we kicked out several categories and scenarios in the converging part. The main challenge here was to identify these new categories, as categories and scenarios from the workshop did not necessarily create a well-defined space. As such, while focusing on the categories provided by the participants, we revisited our meta-discussion principles from audio noise cancellation and the human visual system. In audio noise cancellation, audio noise is typically categorized not by its source, but by the frequency domain. Besides the character of the stimuli, we also saw differences in the impact and visual noise can have on the affected individuals. For example, some stimuli cause affected people to be absolutely overwhelmed and almost unable to perceive other information and consequently perform their normal actions, which addresses the need to compensate for those noises. Finally, we built a two-dimensional visual noise space. Here I explain how the space works. As visual signals are more complex than audio noise, defined as low frequency or high frequency, we give three categories from source stimulus or frequency domain. Spatial noise, which is caused by the structure or location of the stimuli. Temporal visual noise is caused by change or variances in stimuli over time. Waveform visual noise is directly caused by the frequency and intensity of the visible light as perceived by the viewer. It is worth pointing out that the identified categories for visual noise are not mutually exclusive, as some sources have properties that overlap with several categories. Besides the character of the stimuli, another category that emerged was the visual impact, as we saw differences in the impact the visual noise can have on the affected individuals. When visual noise becomes so prevalent that it starts to overwhelm our visual sensing and prevents the sense from functioning properly due to an increased perceptual load, we called this category the overwhelming visual noise. Another category, which we called interfering visual noise, is those that directly interfere with humans and their visual system to the extent that they can still perceive their environment and can perform tasks but with reduced performance. To better show how this space works, I picked two examples. People moving while you are studying should be categorized as temporal and interfering visual noise. The scenario describing being blinded by headlights should belong to waveform and overwhelming visual noise. However, there are several limitations in this visual noise space. First, there are also some categories and scenarios mentioned in the workshop but not being added to our visual noise space, like the natural and artificial light, because we hope to keep the model easy and visual noise cancellation inspired. On the other side, the finding of the subjective nature of visual noise raises a problem, as we cannot be sure of having covered all visual noise descriptions and scenarios. But we saw a high saturation in the results from our initial workshops, and similar scenarios kept on getting repeated. And there are also different categories ways. This one we consider the perceptual system in our model. However, using frequencies of noise does not map well against it. We believe that alignment with the underlying processes may be beneficial to targeted investigations of sources and counteractions. We then built prototypes to compensate for visual noise and ran an explorative investigation to provide initial feedback on the concept of visual noise cancellation and developed prototypes. Similar to audio noise cancellation headphones, we built visual noise cancellation headphones to compensate for visual noise. We built the prototype based on Oculus Quest 2 as the head-mount device and Zip Mini as external word cameras, given that Quest 2's see-through mode is grayscale and low resolution. Please refer to the paper for more details about the prototype. It is worth pointing out that the prototype provides pathways for visual noise that are not caused by impairments, but by sensory impacts. As a practical implementation of visual noise would not fully decouple the users from the environment, we are also utilizing a better system that resembles traditional glasses or vision aids, such as optical see-through head-mount device. To collect the initial feedback on the concept of visual noise cancellation and the developed prototypes, we then conducted a within subjects qualitative user study with 13 participants, mostly from the workshop. The general idea was to test our concept of visual noise cancellation by simulating the 4 typical detailed visual noise scenarios that arose from the workshop. As a result, some people thought the visual noise cancellation mode was more pleasant and less harsh. They mentioned that they could see details better. People also suggested that using the visual noise cancellation mode in a gallery and highlighting a person in concert would be interesting applications. However, some participants also expressed that it introduced new noise due to replacing the color rather than reducing the size of the glare. And only 6 of the participants actually identified the cold light as a source of noise, with 3 mentioned it generated anxiety, which proves the findings in the former workshop that visual noise is highly subjective. For more interesting findings, please refer to our paper. To conclude, we found that participants have had different ideas, but we still saturated with the term visual noise. We can clearly give a positive answer to the question if there is something such as a sensitization of visual noise. We also gained a deeper understanding of the notions of visual noise and the real-life scenarios. It's also clear to see that visual noise is highly subjective. We rarely found a consensus among all participants. However, participants commonly preferred visual noise cancellation, even less affected by the noise. We can expect that not everyone may respond and certainly not respond in the same way to specific visual noise, and therefore will not benefit from cancellation. Importantly, we also found from the exploratory study that all forms of visual noise cancellation found some spot, showing the general potential for visual noise cancellation. In the future, we plan to extend it into more technologies like optical see-through head-mount device, and we also plan to run more targeted user studies, like quantitative studies with eye-tracking methods. Thanks.